Hi there. In this topic, we're going to deal with the different types of bridges and how different forces might work on a bridge. Just as a gentle reminder, last time we talked about different types of loads. Structures have what's called the static load, and the static load has to do with the weight of the parts of the structure, and this never changes on a structure. So the static load is the beams of this. It would be anything that was a permanent fixture on the structure. Second kind of load that we need to worry about when we're building structures is something called the dynamic load. The dynamic load is always changing, so traffic that goes across the bridge, like this cat, would be considered a dynamic load. Or external forces like winds or tornadoes, these are dynamic loads. And so when we build structures, we want to, of course, have them combat the static load, sometimes called the dead load. And they should also combat the dynamic load, or sometimes called the live load on a structure. Let's look at bridges and deal with the different types of bridges. In particular, we want to talk about what makes bridges stay up and fall down, the different types of bridges, and then eventually you're going to design and construct your own bridge. So there are four major types of bridges. The first type is something called a simple beam bridge, which is just a horizontal block supported by pillars or columns. So here's an example of a simple beam bridge going across a river in England. Here's another simple beam bridge going across here. Here's another simple beam bridge for highways in Germany on the Autobahn. So we have pillars or columns that hold up the deck of the bridge, and that's it. That's all it has for support. One thing you have to be careful of when you're building a simple beam bridge is the following. Here's the beam itself. And what happens is when there's forces subjected to it, it starts to bend. And the middle of the beam, right here, this dotted line, if we measured the length from here to here, compared to the length from here to here, when it had no stress, the middle part where my pen is going would not get bigger or smaller. However, let's say we measured the length of the top, which is the distance from A to B. So let's measure the distance from A to B when it's not under stress and compare it to when it's under stress. What would we notice about this distance? Well, it's probably about, if I took my ruler, it would be about 15 centimeters in length here when it's under stress, and here it would be only 13 centimeters if we took our ruler. And let's take distance C to D on the bottom and compare that to distance C here and distance D here. What would we notice about CD here compared to CD here? This distance here, of course, is 13 centimeters. But what would we notice when it's under stress? It would be longer, so it would be 15 centimeters. And sorry about this, let's change this. This wouldn't be 15, this would be something like 12 centimeters. So from CD here to CD here, all of a sudden it got longer. It got stretched. If it got stretched, we'd say it's under tension here. And from AB to AB here, remember I changed the number, it's about 12, it got squashed, so it would be under compression. But not in the middle. The middle is what we call neutral. It's the neutral axis. Because of that, we've built beams that we can shave out the middle part. We call this an I-beam. Notice the shape of an eye. And an I-beam, like this massive I-beam that they're moving made out of cement, has no neutral part, no middle. And that doesn't make the beam any weaker. In fact, it makes the beam stronger because the beam is lighter now and just as stiff or strong. Here are arch bridges, another type of arch bridge. Arch bridges make use of wedge shapes, and the center is called the keystone of the arch bridge. So there's the keystone. And the keystone has the weight of all these other ones kind of leaning in on it. Arch bridges are pretty strong and they withstand compression. There's another arch bridge, another arch bridge. Then there are truss bridges. Truss bridges have triangles that are hinged together to make them really strong. There's another truss bridge in Japan. And why are trusses so common? Trusses can be arranged in so many different triangular shapes is one thing. And they're experiencing compression and tension that counteract each other, okay, and balances each other out. Here's another truss bridge. The most common type of traffic that goes over a truss bridge is usually a train. Trains are really heavy. Finally, there's cantilever bridges where the beam is supported at one end. Not finally, but there are cantilever bridges where the beam is only supported at one end. So drawbridges, for example, are cantilever. And then there are suspension bridges where cables hold up the bridge deck. Suspension bridges. The cable is made by running spools of smaller cable back and forth across the towers. This is called spinning the cable. So suspension bridges. What kind of bridge would this be? It's a cantilever bridge. It would open up and allow fish, allow ships through, and it's only supported on one side. What kind of bridge would this one be? Even though there are cables, this is a truss bridge, really strong. What kind of bridge is this one? Probably categorized as an arch bridge. Another arch bridge. Another arch bridge. This is a truss bridge. Truss. Probably simple beam. So let's talk about our 4 kinds of bridges that we've looked at and categorize them from strongest to weakest. So the truss bridge is by far the strongest. Train traffic, for example, would go over a truss bridge, and the indication that it is a truss bridge would be the triangles, which are really strong shapes. The second strongest would be a suspension bridge, where the cables, which are in tension, and the columns are in suspension or compression. Maybe the third strongest would be the arch bridge. Again, the keystone helps diminish all the force down towards these strong. You'd have to have great big huge columns here. And then the weakest is the simple beam bridge. Let's look at a video clip about bridges.
When a train crosses a truss bridge, the heavy bottom members are always in tension and the top members always in compression. And depending on the position of the train on the bridge, The connecting vertical and diagonal members will change from tension to compression. But at any given point, these opposing forces stay balanced. A pull on one member is resisted by an opposite push from another, all along its length. So the bridge remains rigid and strong despite its lightness.
And one more video clip. If I can get to it. And it's this one.
Minneapolis 911. At the end of rush hour on a hot summer day in Minneapolis, Minnesota, a major bridge over the Mississippi River suddenly collapsed. Over 100 cars fell with the bridge. And if this bridge collapsed, what about all the others like it across the country?
We have 76,000 structurally deficient bridges in the United States. That's almost 2.5 times as many as we had 20 years ago. And we need more modern, non-destructive technologies to inspect those bridges today to make them safer for the future.
The cause of the Minneapolis collapse is still under a federal investigation, but here's what we know. The Minneapolis Bridge was an underdeck truss arch design made up of twin trusses of steel beams arranged in triangles and connected with steel plates called gussets. The trusses distribute the weight of the traffic throughout the structure, all the parts working together. But the design has no backup against failure. If one major part fails, the whole bridge can come crashing down. Investigators found that 16 of those connecting gusset plates failed, resulting in the catastrophic collapse. The tragedy was seen as a wake-up call, highlighting the need for technology that warns us before a bridge fails. If we could only probe deep inside an old bridge's inner structure to find out which are in danger and which are sound, well, it turns out we can. The same way that submarines detect other boats, using the echoes of sound waves, or sonar. At the University of California, San Diego, they are using a kind of sonar technology to find cracks in bridges. They're called piezoelectric sensors, and they can both send and receive high-frequency tones right through a bridge.
So this one will launch a wave into the structure, while this white one here will then detect the signal at the other end.
The wave is ultrasonic, so Eric's computer converts the signal so that we can hear it.
Alright, so what we have here is our signal that we received on the healthy structure plate. And if we downshift that ultrasonic signal to the audible range, this is what we hear. Very nice, clear tone.
But if you fracture that steel plate, the crack forces the ultrasonic waves to take different paths.
Now we replace that healthy beam with a damaged beam. Put the same sensors on it and apply the same signal again. This is what we get out. You can both see the difference and hear the difference, these extra tones that are now present in that damaged plate.
So how would that work on a bridge? You can place a bunch of these devices around trouble spots like gusset plates, and then have them ping each other in different combinations, probing for problems such as cracks in the structure.
What we do is we deploy arrays of these, many of these on a structure, and then we launch waves and we listen. The idea then becomes, if you keep doing that test and a crack has developed, maybe corrosion has occurred, a bolt is coming loose, or the signature that we're detecting is going to fundamentally change.
But the ideal technology would not only probe for damage and signal its location, it would literally show you where it's broken. At the University of Michigan, researchers have developed a nanotech skin that could one day cover and monitor bridges 24/7. Here, they've successfully tested a coating that, when stimulated with an electric current, senses damage beneath its surface. And the secret of the sensing skin is